Now we want to start to interpret everything here. And as we interpret these things, it becomes really interesting here. So now we want to interpret these relationships. So why do we want to interpret these things? The first thing, what we should do here is that we should rearrange the center of mass of acceleration equation. And the way we will arrange it here is that I'm going to multiply the total mass out. So if I multiply the total mass times this, then this guy is then going to give me the sum of all of the forces within the system, right? So this is all of the forces of the system. But wait a minute, what does that mean? That means here it should be the sum of all of the internal forces plus the sum of all of the external forces acting on the system. Well, check it out. There's something really, really interesting that happens here. And what we find here is that, so for a system, we can look at pairs of particles interacting. In other words, let's go look at my system here. So here's my system, right? So when I look at my system here, I have pairs interacting. So let's focus on two pairs. Let's say that I have a pair, right? I have a pair 1 and I have a pair 2. So what do they do? When these guys interact, actually, I'm going to change colors on these guys. So there's red 1 and green 2. What you're seeing here is that red 1 is going to interact with green 2, but then green 2 interacts with equal and opposite forces. By the way, I can do this with pair 3 or, pair 4. I'm going to have equal and opposite forces all of the time within the system here. And what that tells us here is that if we only look at the sum of internal forces, Newton's third law says they all sum to 0. Because anytime I have a particle, right? Anytime I have a particle like this guy, particle number 1, and then I have particle number 2, we see that these guys are always going to have equal and opposite forces here. And because they have equal and opposite forces, in other words, F12 and F21, these guys from Newton's third law tells us that I'm going to have the sum of the internal forces is going to be F12 plus F21, but according to Newton's third law, it's always going to be like this. And when it will always be 0. So the sum of internal forces will always be 0, which is a very powerful statement for a closed system. So therefore, the internal forces of any closed system is 0. So in other words, right, What I'm really saying is this, that internal forces do not affect the system's motion. Wait, what do I mean by system? Center of mass motion. But external forces will. And there's lots of examples that we could think about here. Okay, so here's some examples right here. So the first one that I want to look at is that, let's assume the first one is that, let's talk about a baseball. So if I talk about a baseball has zillions of molecules interacting inside, right? There's lots of interactions inside of a baseball. So you could imagine that because of that, we know then that the sum of internal forces of all of those zillions of molecules, because the number of molecules inside the baseball is fixed, what's it going to do? 0. So therefore, they do not affect the motion of the ball. So now we take a baseball, and what we're going to do here is that now one throws it for projectile motion. So you could imagine here is that now, here's our baseball. So I'm going to take my baseball here, and I'm going to, so if I look at this thing, I'm going to come in and I'm going to toss it. So if I toss it here, right, we have a green baseball here. And as we toss it, we're throwing this here. So that what we're really doing here is that now we have an external force acting on the ball, which is going to be the force of the hand. So what's the ball going to do? It's going to follow projectile motion. And of course, what's in projectile motion here, the ball experienced the hand's force, and that's what set it in motion. And then we have what? The force of gravity, and the force of gravity is affecting it. But the molecular motion never affects the ball's motion, right? Never affects the ball's motion. Another one that we could think about here is thinking about that suppose a dad is driving a son to, to a baseball game. There we go. And the daughter wants to get there really fast. So what do we do here? Well, let's imagine that we have a car. So if we're driving a car, right? And what we're going to do in this case here is that we're going to assume that we have a seat, of course, and the son wants to go to the baseball game really bad. So you could imagine here that there is this green dashboard. Okay, so this is a green dashboard. And what is the son doing? So the son is sitting right here, and he wants the dad to go faster, so he pushes on the dashboard. So the son wants to go faster and pushes on the dashboard. Does the car go faster? Of course not. But the question is why? Because look, this is my system. How many particles are in the system? Well, in this case, we have the car, the dad, and the sun. So as the sun pushes on the dashboard, right? So this would be the force of the sun on dashboard. The dashboard is going to have an equal and opposite force. And of course, that means that the internal forces within the system are going to be zero, which means that they do not affect the motion of center of mass, because the internal forces cannot do that. So there's two examples of how we could look at that. So the next thing I want to do here is that now that we're starting to interpret this thing here, right? We were talking about the internal forces. So the only thing that can affect the system then is external forces. The only thing that can affect the system is external forces. So if that's the case here, what we say here is that the center of mass of a system moves like a single particle. The center of mass of a system of particles moves like a single particle. According to what? The external forces. And this I'm going to write as a shorthand like this. And this, according to Newton's second law, tells us that the total mass has the center of mass location here. This is Newton's second law for a system of particles, right? So this is Newton's second law for a system of particles. Of course, in a closed system, okay? But the system has to be closed. But the problem is most systems are closed, right? You're thinking about the sun, the kid, and the dashboard in the car. That's a closed system as they're driving down the road. But the thing about it is that we could continue to look at this thing here. And what I want to do here is that now we can apply this to Newton's first law for a system, right? Newton's first law for a system, what does that mean? Well, what we said about Newton's first law in the past here is that if there are no external forces, if there are no forces acting on an object, then the object will either be in static equilibrium or dynamic equilibrium. A system behaves exactly the same way here. So if the external forces is equal to 0, right? So that means no external forces. Then that tells me that the center of mass of the acceleration must be 0. So we must have a situation of what? Static equilibrium or dynamic equilibrium. And what we mean by this is we mean this, that the center of mass location must be a constant, that the velocity of the center of mass must be a constant. So this interprets then that the center of mass location initially must equal the center of mass location in its final state. The velocity center of mass initially must be the same as the center of mass finally. This is what it means to be.
You can't take a shower
To be in this situation here.
in 5